Hi everyone, in this video we'll be going over solutions to a Calculus 2 exam on techniques of integration. So let's go ahead and look at the first question, which asks us to evaluate a few different integrals. And notice that it doesn't tell us what technique to use, so we have to determine that on our own. Part A asks us to integrate 35 times cosine to the fourth power times sine to the third power dx. So what we're going to do here is we want to rewrite sine. I'm going to factor out 35. And sine cubed, I'm going to rewrite as sine squared x times sine of x. And then I can use the Pythagorean identity to rewrite sine squared. From here, I'm going to go ahead and use u substitution, and I'm going to set u equal to cosine of x. And then that will make du equal to negative sine of x dx. So coming back over here, we have 35 times the integral of u to the fourth times 1 minus u squared, and then negative du is equal to sine of x dx. So this here I will replace with negative du. I'm going to go ahead and factor out the negative sign. And I'm also going to distribute in u to the fourth. Now we can start to integrate. So we have negative 35 times u to the fifth power over 5 minus u to the seventh over 7 plus our constant of integration. And then finally we want to plug back in u. And there is our final answer for part A. All right, let's move on to example or question B. And for this question, we need to use trig substitution. So I'm going to go ahead and let x equal 5 sine theta. And that's going to imply that dx will equal to 5 cosine theta d theta. So let's go ahead and rewrite our integral now. We have the integral of 1 over 25 sine squared theta times the square root of 25 minus 25 sine squared theta. And then dx is getting replaced with 5 cosine theta d theta. This is equal to the integral of 5 cosine theta d theta over 25 sine squared theta. I can factor out a 25, and that's going to leave us with 1 minus sine squared theta. And if I use the Pythagorean identity, I can rewrite that as cosine squared theta, and then if we take the square root of that, then that's going to leave us with 5 cosine theta. Then the 5 cosine theta in the numerator and denominator will divide out, and I'll factor out 1 over 25, and then we have the integral of 1 over sine squared d theta. And using the reciprocal identity for sine, I'm going to rewrite this as cosecant squared theta, and the antiderivative of cosecant squared theta is negative cotangent, so then this becomes negative 1 over 25 cotangent theta plus c. And now I'm going to go ahead and draw a right triangle. Here's theta. I know from the beginning that x is equal to 5 sine of theta, which implies that sine of theta is equal to x over 5. So that means that our opposite side length is x and our hypotenuse is 5. And if we use the Pythagorean theorem, then the adjacent side length would be 25 minus x squared to the 1/2 power, or the square root. So then coming back here, we have -1 over 25. We know that cotangent is equal to tangent's equal to opposite over adjacent, so cotangent would be the reciprocal of that. So it'd be the square root of 25 minus x squared over x plus c. And maybe I'll just combine that into a single fraction. So we have equals the square root of 25 minus x squared, negative, and then over 25x plus c. So here is our final answer. In part C, we have the integral of p to the 4th times the natural log of p dp. And here we have the product of two functions, so it might be worth trying integration by parts. And remember, we have the acronym LIATE, and the L in LIATE stands for logarithm. So let's go ahead and make u equal to the natural log of p. If I take the derivative, we'll get du is equal to 1 over p dp, and then dv will equal whatever's left over. And so v is going to equal p to the 5th over 5. So remember, the mnemonic device for integration by parts is ultraviolet super voodoo. So we have p over 5, or excuse me, p to the 5th over 5 times the natural log of p minus the integral of p to the 5th over 5. And then we want to multiply that by du. Okay, and then that would simplify to p to the 4th over 5. So let's factor out 1/5. And then we have p to the 5th over 5 times the natural log of p. I'm going to increase the power by 1 and then divide by that new power. So let's go ahead and simplify that. And then plus our constant of integration. So here's our final answer for part C. Question 2 says, use the trapezoidal rule and n equals 5 to approximate the definite integral from 1 to 6 of 5 over x dx. If you need a refresher, here's the formula for a trapezoidal rule. So let's go ahead and calculate delta x. We have delta x is equal to b minus a over n, which is equal to 6 minus 1 over, and our n value is 5. So this is going to equal 1. So the notation we use is capital T sub 5 is equal to delta x over 2 times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3 plus 2 times f of x sub 4 plus 2 times f of x sub 5, and then plus f of x sub 6. All right, so delta x was equal to 1 from our earlier calculation, and we know that f of x sub 0, x sub 0 is our a value, which is our lower limit of integration, so that's 1. x sub 1, because our delta x value is 1, that means I'm going to add 1 to 1, so our next x value is 2, and then 3, and so on, and then our last x value. I'm realizing there's an error here. I added one too many x values. So that should be f of x sub 5. Okay, so x sub 5 is going to be our b value, which in this case is our upper limit of integration, and that is 6. So I'm going to go ahead and fill in this formula down below now. Okay, so we're at this stage. I want to go ahead and plug in these x values into our function now, where f of x is equal to 5 over x. So I'll go fill those out really quickly. So I went ahead and I plugged in 1 through 6 into our function, and we have those numbers inside of our brackets. We're simplifying that so we get 1/2 times 56 over 3. And finally, if we reduce our fraction after multiplication, we get that our final answer is 28 over 3. So that is our approximation for the original definite integral. Question 3 says to evaluate the improper integral from 4 to infinity of 1 over x minus 2 times x minus 3 dx. So our integrand here is a fraction where we will need to use partial fraction decomposition. So I'm going to go ahead and take our fraction here. And our goal is to write this as capital A over x minus 2 plus capital B over x minus 3. And I'm going to go ahead and use the method of clearing fractions. I'm going to take this entire equation and I'm going to multiply every term by x minus 2 times x minus 3. If we do that, then we get x minus 2. No, just kidding. We'll get 1 equals a times x minus 3 plus b times x minus 2. So from here, I can go ahead and plug in special values of x. So I'm going to go ahead and let x equal 3. And then if we do that, we get 1 equals b times 3 minus 2. The a value is going to cancel. And so out of this, we get b is equal to 1. And then I'm also going to let x equal positive 2. If we do that, we get 1 equals a times 2 minus 3. And then the b value will disappear. And so this is going to end up producing that a is equal to -1. So based off these calculations, what that's going to allow us to do is it's going to allow us to rewrite our original improper integral as the integral from 4 to infinity of -1 over x minus 2 plus 1 over x minus 3 dx like that. Okay, so I'm going to go ahead and integrate both of those, and this is going to equal the limit as b approaches infinity of negative natural log of the absolute value of x minus 2 plus the natural log of the absolute value of x minus 3. And we are evaluating this from x equals 4 to x equals b. Now, one thing that I can do that's going to make our life a little bit easier is that these are both natural logs, and so I can condense this using one of the laws of logarithms. So this is equal to the limit as b approaches infinity of the natural log of the absolute value of x minus 3 over x minus 2, like that. Okay, at this stage, I can split this up into two different limits. So we'll have the limit as b approaches infinity of the natural log of b minus 3 over b minus 2, like that, minus the limit as b approaches infinity of the natural log, and 4 minus 3 is 1, and 4 minus 2 is 2. So we have that. Now, if you don't remember this from Calculus 1, if you're taking the limit of a continuous function, which the natural log is a continuous function, and at least what we can do is we have the ability in that first limit to bring the limit on the inside of the natural log. So this is equal to the natural log of the limit as b approaches infinity of b minus 3 over b minus 2. And we have the limit of a constant, so that's just going to be that constant. So we have minus the natural log of 1/2. 1/2 is a positive number, so I'm going to go ahead and drop the absolute value bars. From here, this thing is a rational function where both the degree of the numerator and the denominator are the same, and so the limit is going to equal the ratio of the leading coefficients, which in this case is 1 over 1. So our first limit is going to end up equaling the natural log of the absolute value of 1 minus the natural log of 1/2. And the natural log of 1 is 0, so this ends up being negative natural log of 1/2. And you could also see that the coefficient is a -1. And so if we wanted to, we could use logarithm properties to bring that -1 inside and have it as an exponent. And so that's nice to rewrite it like that, so we don't have to deal with a negative sign or a fraction because the reciprocal of 1/2 is 2. So our original improper integral converges, and our final answer is the natural log of 2. Question 4 says determine whether the following integrals converge or diverge, provide sufficient reasoning. So part A, we have the integral from 0 to 1 of e to the x over x squared dx. Now, this is an improper integral because our lower limit of integration is 0, and this function has a vertical asymptote at x equals 0. So we want to figure out, does this thing converge or diverge? And so we're going to use the direct comparison test for integrals. And so I know here that x is on the x is on the interval from 0 to 1. And so if I thought about the graph of just y equals e to the x, that looks something like that. And I know that if I plugged in 0 into that function, this ordered pair right here is 0, 1. And so if I'm plugging a number into this function that is at least 0, then the output is going to be at least 1. In other words, on this interval, we have that e to the x is greater than or equal to 1. Now, what I can do is I can take this inequality and I can divide it, both sides of the inequality, by x squared. Now, on this interval again, x squared is always a positive number, and so we don't have to flip the inequality symbol. We know that e to the x over x squared is going to be greater than or equal to 1 over x squared. And so essentially from this, from the direct comparison test for integrals, we have that the integral from 0 to 1 of e to the x over x squared dx has to be greater than or equal to the integral from 0 to 1 of 1 over x squared dx. Now, please be very careful. The integral on the right-hand side, this one,
You might be tempted to use the p-test, but we cannot use the p-test on this because our upper limit of integration is not infinity. So that's not how we would go about doing this question. We need to rely on something else.
Okay, so I have the integral from 0 to 1 of 1 over x squared dx. I'm going to rewrite this as the limit as a approaches 0 from the right-hand side of the integral from a to 1 of 1 over x squared dx. This is going to equal the limit as a approaches 0 from the right-hand side of, if I take the antiderivative of 1 over x squared, we get negative 1 over x, and I'm evaluating this from x equals a to x equals 1. If I go ahead and plug in the limits of integration, we have the limit as a approaches 0 from the right-hand side of negative 1 over 1 plus 1 over a. And so if I take the limit as a approaches 0 from the right-hand side of just 1 over a, that's going to end up equaling negative infinity. So that's negative infinity. That means that the improper integral on the right-hand side diverges. So this diverges by, or why don't we say because, of our above calculation. Then we could say, therefore, because the integral, our original integral, has to be greater than or equal to that, therefore, by the direct comparison test for integrals, this integral must also diverge. And there is our answer for part A. For part B, we have the integral from 1 to infinity of cosine squared x over x squared dx. And in this question, we are once again going to use the direct comparison test for integrals. So here we have our x value is on the interval from 1 to infinity. And I know that cosine of x is less than or equal to 1. And if I were to square both sides, I know that cosine squared x has to be less than or equal to 1 as well. And x squared is going to be a positive number, so I can take my inequality and divide both sides by x squared, and the inequality sign will still hold true. So in other words, cosine squared x over x squared is less than or equal to 1 over x squared. And so in this scenario, because of the direction of our inequality sign, and 1 over x squared being the larger function, what I want to do is, this implies that the integral from 1 to infinity of cosine squared x over x squared dx is less than or equal to the integral from 1 to infinity of 1 over x squared dx. And it's sufficient here. We know that this converges by the p-test because p is greater than 1. Here our p-value is 2, so I know that that's going to converge. So therefore, by the direct comparison test for integrals, the integral from 1 to infinity of cosine squared x over x squared dx must also converge. And that completes this question and our exam solutions in this video. Thanks for watching.